This is the risk assessment for making the Voltaic pile. A few hazards include vinegar, the copper ions, copper wire when stripping the rubber back, and the scissors. This is my Voltaic pile. We've got copper coins, an LED light, so hopefully we can power that. We've got alligator clips to connect the wires to the LED. We've got frayed wires at one end and the other end to connect to the alligator clips. A pencil and scissors to cut out the cardboard and aluminium. In my first trial, I used vinegar as the electrolyte, which was acetic acid. It read about 3.3 volts, which was great. However, because of the acid, it caused other reactions within the redox reaction. For example, the copper coins after the experiment showed signs of oxidation, with bluey-green colouring appearing all over the side of the coin that was exposed to the electrolyte. Instead, to combat that, I used a salt water solution, just to make the chemistry explanation a bit easier and to see if the LED would work. Anyway, the pile starts with the copper coin, which is the cathode, then the electrolyte, and then the aluminium, which is the anode. And then we'll repeat this process until we have a stack of about 10 of each material, so that we can generate enough volts to power the little LED. After a few attempts, well actually many attempts with the vinegar battery, I eventually got it to work with the salt water battery, which was great. As you can see, it's pretty dim, but you can see that the LED is alight, which was a success. My research showed that you needed around 1.7 to 2 volts to power a red LED. So in my first few attempts with battery 1, I reduced the pile to about 1.8 volts, and it wasn't successful. Then I thought maybe the wires could have had quite a lot of resistance, so instead I used a larger Voltaic pile, and it was successful. The voltage reading for my salt water Voltaic stack was around 4.1 volts, compared to this battery, which was a week before, which is the vinegar battery. It was only about 3.3. When I increased the pile, it turned to 3.4, and when I decreased it, it would obviously lose voltage, which shows that if you increase the pile, you also increase the voltage. In this experiment, the salt solution acts as the electrolyte containing ions. The ions will react to the two different metals and form electrons. Now you have electrons. The second thing that's needed is the movement of electrons. This is called the current. The two metals react differently. One metal attracts electrons, the other metal loses electrons. The different charges allow electrons to move, creating the electric current. Now to explain the battery in more depth. I wanted to base my Voltaic pile on a classic galvanic cell, otherwise known as the Daniell cell, with zinc and copper. However, I used aluminium instead of zinc because we didn't have any. Using a Voltaic pile instead made the chemistry much more complex, because the electrolyte was not similar to the metals in any way. Now, to explain the redox reaction, we'll take one cell of the Voltaic pile. We'll start at the aluminium. The aluminium is more reactive than copper. That makes it oxidize. The oxidation reaction at the anode is as follows, with the aluminium losing 3 electrons, because it came in contact with the hydroxide from the water. The aluminium atom goes to aluminium ions and 3 electrons, which move into the wire, leaving the aluminium hydroxide as the product. From the electrons that moved through the wire, they then reach the copper coin. Now at first, I thought that the cathode is supposed to reduce. And yes, I thought this would be the case, but after a bit of reading and some funky science videos, I learned that the copper conducts electrons. They are just passing through to the oxygen in the water molecule from the electrolyte. And this is where reduction happens. So yes, you could argue that it occurs at the cathode, but not in it. The reduction equation is as follows. The oxygen that has dissolved in the water has gotten its electrons via the copper coin from the wire. The electrons are then carried back up to the aluminium by the hydroxide ions produced. And that's where the hydroxide ions come from in the oxidation reaction. And then it's just a big loop, and again and again. Now you might be wondering what the sodium and chloride ions are doing in this. Well, those ions are there to balance the charges out after the redox reaction occurs. When I was taking the pile apart after the experiment, I noticed there was black deposits on the copper coin. I thought it was similar to the vinegar reaction where I saw blue copper ions, so I researched and found that it could be black solid copper oxide. This means that there were other reactions happening at the time. To solve the half equations, we start by making them common. I think of common denominators in maths for this step, so timesing one by 4 and the other by 3. Once we have times all through, we can add them both together in one equation. Then there are a lot of cancels that appear, and we can simplify, and then we have one final equation. That concludes the explanation of the battery.